This session on storage, we have the pleasure to have Simon Tindemans from Delft University, who's going to talk about optimal dispatch of heterogeneous batteries. So more batteries. Huh? Okay, you have the floor.
Thank you, René. Good morning. Yes, indeed, more batteries, but a very, very different take. We had something similar in mind and ended up taking a different turn and ended up in a very, very different place. So it will be a nice comparison, I think. So the work I'll be presenting here is, for the most extent, done by PhD student Michael Evans at Imperial College. He's in the back here. We'll be looking for a job later this year, so if you like this, go and talk to him. Also involved is David Angeli, his supervisor at Imperial College. So we've heard already on Tuesday that 2019 is the year of flexibility. Ben Godfrey mentioned that. I don't need to reiterate the point, just saying that flexibility can come from many different resources. It can come from traditional power plants, it can come from dedicated batteries, it can also come from all kinds of residential things, whether that's batteries in the home or whether that is actually flexibility in demand that is then represented by a battery. So this flexibility exists on all kind of levels. It exists on the level of generators, where we have large units, and these are kind of approximate GB kind of numbers, right? So you have very few very large numbers. You have quite a few more potentially things in this scale, and you have pumped hydro in there, etc. You can go industrial commercial demand response, and you get to residential demand response, kind of into the long tail of things that are here, which frankly I think are really where at least the science gets interesting. But where the economics is best, that remains to be seen. So as was already mentioned by Anna, Anna Scaglione, is that the flexibility can often be described by a battery. So you have all kinds of flexibility, but ultimately a lot of the models would be similar to a battery. Just a few examples of the various types, again, to illustrate this point. Pumped storage here, the Norwig in Great Britain and Wales. Various types of fuel storage, so this is not charging, this is discharging only. We'll cover that case later, right? So you just have your aggregator, that's some form of storage. You have your fuel tank sitting there and it generates for you. So it's energy limited storage. UPSs, favorite of mine for those who have seen me speak before. Fridges, I like fridges, just like Sean. And Anna. Yeah, I didn't do pool pumps, but they're the same. And these large grid scale storages. We don't have so many pools in the Netherlands. Great Britain is just maybe climate change will get more pools and things. We'll sort out. We'll see. So this is the scope for this talk. And this really, as I mentioned, it started as a small kind of toy model, and it turns out that it was way more interesting, had more depth than we thought at the time. So if we consider a heterogeneous fleet of storage units, and we don't do economics here, but we try to maximize their contribution to security of supply, right? So we are in a shortfall situation. How do we dispatch them? And how do we use this knowledge then in operational planning and planning timescales, right? So going from operations way out. So a couple of scenarios just to illustrate this point where it might actually be relevant. So you might have a microgrid that's usually grid connected, but the grid connection gets interrupted. How can it best schedule its resources, which might be, it could be even at a hospital, right? It could be as diesel generators. How would it schedule them to last as long as possible until grid connection is restored? Or an aggregator that supplies frequency response services to the grid of various sorts, right? So it wants to make sure it can deliver. Or a case we'll discuss later, if we have the use of batteries for system adequacy, right? So where batteries are used as a last resort, right? How do we quantify the contribution these batteries can make to the system security supply in that case? And finally, for example, within a single electric vehicle, if you were to have heterogeneous batteries in there, how would you manage them to maximize your chances of actually arriving at a destination and instead of kind of running out of power halfway, or somehow in some other way limiting what the user, the driver wants to do with the vehicle. So these are the kind of scenarios we look at, and I'll start with a little motivating example just to illustrate this. So suppose we have three options, right? So we have, I'll give you three options. I'm going to get some audience participation here. Three options. We have one with this unit, so we have energy and power, right? So defined by energy and power, and we do discharge only. And we have this one for a total power capability of 22 kilowatts and a total energy rating of 144 kilowatt hours. Or we have this option, which is a single battery. So these are the same. Or we have a third option, which is again a combination of two batteries. So I'm going to ask you which one is best. Who votes for A? Okay, we have an A. Who votes for B? Okay. Who votes for C? Lovely. Okay, so we have lots of C's, that's nice. Anyone for it depends? always a good answer, yes. It's always a good bet, it depends. But okay, we'll come back to this later. Right, so here's the outline of the talk. First I'll define this problem in a bit more detail, then go from an optimal control strategy that we devised for this problem, and then go from there into a summary representation of what the aggregate flexibility of a set of batteries would be, and from there into this example of contribution to system adequacy. So we'll take this from operation to planning and then wrap up with a few remarks at the end. So if you want to read along, there's three papers we published, or at least one is a paper, the other two are an archive. And here I should mention that it turns out that sometimes ideas have reached their time, and it happens that people work on the same thing. So we found out actually, James Cruz and Stan Zachary here in the audience, they were simultaneously doing pretty much the same thing. So I would say if you're interested, read this, but also for an alternative take, read this too. Results are slightly different, but basically, well, and largely identical, and they make the same points. So it's worth reading that too. Okay, so problem definition. So we are making some very heroic assumptions here, but they are valid or approximately valid in some of the cases I mentioned, we believe. So first we focus on security of supply, so we assume that the cost of unserved energy is much larger than anything else, right? So this is markets to some extent go out of the window, and we say, ultimately what we want is we want to serve the customers of this system. And we focus on discharging only. So this is, of course, in some cases it's literally true, in many cases it's not, but we focus on the behavior during an actual supply shortfall event, right? So once you're in a situation where you need extra power and you are using the batteries, how then do you manage those this discharging? Then we assume there's no cross-charging between batteries as well as part of that, right? So that turns out that can sometimes be a good idea, but we don't do that now. And this also naturally applies to cases where you have fuel constraints, actual fuel constraints, like a finite jar of diesel, or finite bucket of diesel to supply. Okay, so those are assumptions. So with those assumptions in mind, and again, I won't go into a lot of mathematical detail in this talk. For that, read the papers. I'll give you the hand-waving version of some of the proofs here and some intuition on the solutions. But we have a set of devices, 1 to n, each of which has a maximum power output given by this pi bar. There's a state of charge in each device, energy. This incorporates losses, right? So we say the energy in the device is the amount you can actually deliver, right? So whatever is stored, but this is the amount that can come out. But we'll, instead of working directly with the state of charge, we work with this state x, which is the time to go, right? So we divide by the maximum power output. We say how long could this battery run at maximum power for, right? That is the representation of state of charge we use, which turns out to be really convenient. We have our control parameters ui, which is the power delivered by the battery. Simple, so between 0 and this maximum power output, and that gives rise to this state dynamics, right? So the rate of change of the duration at which you can run is the amount of power divided by the maximum power. That's it. So then the aim of what we try to do is we try to satisfy this thing called a power reference, right? So this is a request coming in. Somehow the user wants to satisfy this this amount, and we aim to satisfy it, which means that the sum of all powers delivered, from each individual battery sums up to that total, right? So then we are, then everyone's happy. Okay. So this is the visual language, just very briefly, just to, because I'll be coming back to these pictures quite often. So here we have this kind of reference, right? So we have power as a function of time, and we'd like to see whether we can meet such a reference, which will be subject to a little or a lot of uncertainty, right? And we'll try to specifically look at the case where there's a lot of uncertainty. And then this is our kind of visual picture, right? So here we have our batteries with horizontally the amount of power they can deliver, right? So this is power capability, maximum power. So I should write, forgot the bars on here, right? So this is the maximum power capability. That's the amount of time on the vertical axis, and therefore, obviously, the surface is the amount of energy stored in the battery, right? So these are three different ones. Okay, so this is the setup. Now we go for how we use this to optimally control the system. And these are the questions we ask. So first is, assume we have a given set of storage units. Can we satisfy this power request in any way? And what do we need to know about this power request in order to decide on the optimal action? And it turns out we need to know very, very little. So the objective is to define a policy that maximizes the ability to satisfy this partially unknown power request. Okay. Basically, if you think about this for a while, I'm just going to present you with the answer first, and then I'll show you why the answer is the answer. Right? So the simple idea is to use batteries with the largest time to go first. Right? So this is, I guess, if you think about it, the intuition is kind of clear, but we'll get here. So to illustrate this, let's suppose we want to satisfy this kind of reference, right? So that's over here. We start a bit low, we go higher. Now what I've done here is I've stacked these batteries. So I've had these same three batteries. I've stacked them from in order of decreasing time to go, right? So this one has a lot of time to go. I didn't put any arbitrary numbers on here. Stack them in this order. Now first, I try to satisfy this request here. So it starts out, all right, nearly 10 kilowatts. Well, I can supply that using the first battery and part of the second battery, right? So what I'll do is I'll try to, as much as possible, use this, get this from the first battery, but of course there's a limitation in the amount, in the rate at which it can decay, because that's actually 1, right? The maximum decay rate here, or the maximum decrease rate is 1, because it's 1 unit time per time, right? That's what happens here. So you take as much as you can from here and a little bit from here until you reach this power level. Now a little bit later, you're still there. And what has happened in the meantime, these two have equalized, right? So this one has reached the same time to go as the second battery, and they're both equal, and you both use them as you can. And you can still supply all load using these two batteries. Now at some point later, you'll see here, power goes up. And now we need the third battery, right? So we then move on and we use a little bit of this battery, and these decrease a bit further. Right, so that's all there is to it, to this simple policy. And it turns out that this indeed is optimal, as I'll show you, in some sense. So this is how you can explain it in terms of mathematics. So what we do here is we basically order the devices in groups of decreasing time to go, and we then can compute this factor at which they will run, right? So the fraction of their maximum output at which they will run, and we have basically 3 groups only, right? So everything, so what it says here is if the power, basically if these devices are to the left of the power requested, run them at full power. If they are to the right of the power requested, don't use them. And if they are at the power requested, run them fractionally in order to make the whole sum work out. That's really all there's to it. And then you get the closed loop dynamics that's given by this equation, right? So where z is the solution, you decrease the time to go by this fraction, and here's the power this is the diagonal matrix just with the powers of each individual battery in there. Right? So that's the definition of this policy, and it has a number of interesting properties. So we've seen already that it equalizes the time to go between devices, and it maintains the order of time to go between devices as well. But this final one really, I think, gives you the intuition about why this works and why this works well, because we can quantify this quantity called maximum instantaneous power, right? So what's the maximum instantaneous power we can deliver if there's a spike, in this case, through some unknown process, right? We don't know what is coming up. Well, basically the maximum instantaneous power is the sum of all maximum powers of the batteries, assuming that their state of charge is not zero, right? So basically the idea is, if possible, keep a little bit of charge in all batteries. So how do you do that? Well, of course, you start using these preferentially, and everything to the right, which has relatively small amounts of energy stored, try to not use them. That's the thing. So essentially you want to be ready for the spike when it comes, and that's the intuition why this policy is optimal. Okay, now a bit more in a bit more detail. We can also see this in terms of what we call a feasible set, right? So we can say, well, a request PR is feasible if there exists any feasible control signal that will allow us to satisfy it, right? So some requests will be infeasible, but the question is, the challenge is that if a request is feasible, given full knowledge of the future, right, perfect foresight, to make it feasible even if that foresight is missing. So this feasibility condition that implicitly defines the feasible set, right? The feasible set is a set of all requests, so function space, the set of all possible requests that can come that are feasible, right? So we have the set of all possible requests, and in there is somehow the feasible set. And we say, well, the size of the feasible set is some approximation of future flexibility, right? Especially if we don't know what will happen, we try to maximize this set. So it turns out that this policy that we describe has the following properties. It maximizes this feasible set at any point in time, right? So that's kind of the proof goes through there. You can show that actually doing this policy maximizes the feasible set regardless of any measure you put on the likelihood of these functions, which actually means that it's a greedy policy that is optimal regardless of what comes, which is really nice. Also, typically, if a signal that you follow starts out with a power level that you can satisfy, and you keep on asking for more, at some point it will turn infeasible, right? So you start out feasible, and as time goes on, you kind of move out of the feasible set into the infeasible set. So by maximizing the feasible set, what we also do is we maximize the time to infeasibility, right? We push out this boundary as far as we can by operating with this policy. Right. So we can, that's a simple example. We can run this and we can get a number of, we can run this against this is a request that's somehow random. And we can compare three policies. So we have our optimal policy. We have two comparison policies. One is lowest power first. So you run the small units first in order to keep the big ones in reserve. That's kind of a heuristic. Or proportion of power, you kind of run all the units in proportion to their amount of power. And what you can see here, we track two things. So what you can see, so these thetas here are the point at which this policy fails to meet the request, right? So we see here, both others fail right around here, and then here this optimal policy, because it's optimal. I mean, this is of course just illustrating the point because the mathematics proves it's optimal in this sense, but it's actually the last one to fail. But what's interesting also, if you plot the largest available power here, right, you see that these others start running out of, so this is a very large population of heterogeneous batteries. I forgot the exact number. I think it's hundreds or thousands. Some of them start to run out of energy at the beginning. So whereas this policy basically keeps all batteries filled to some extent, so it doesn't fail at all, and then it fails catastrophically. At the end, everything runs out, right? At the same time, all batteries are empty. but by doing so it maximizes the time to failure. Okay, so this part what I've shown is kind of a myopic algorithm that's greedy and maximizes flexibility regardless of what happens in the future. So it's optimal both for deterministic and for stochastic applications, right? In this discharge only setting. Right. Let's move on. How do we use this? So we take this setting of an aggregator, right? So we now have an aggregator, controls a fleet of devices. And we've seen already some examples on interesting ways to control aggregate devices. Turns out that often it's nice if you can, well, the way we think about this is if you can separate control and scheduling somehow, right? So some of these aggregate dynamics in fridges and pool pumps, etc., they have this, right? You can create a control signal, and then you have some kind of local control that implements that. So actually, this approach is really well suited to something similar, right? So we have something that looks only at the now and implements a locally optimal control, right? But suppose we are an aggregator and we bid on some kind of market for some, say, frequency response product. So we want to investigate, well, what are the class of signals we can satisfy with our product, right? So how do we, in order to do so, what it needs to know what the feasible set is, right? So it can use this optimal policy, but it still needs to know what the feasible set is. Now, what I've just given you is an algorithm, right? I've given you a policy that says, okay, if this, then that, if this, then that, So that's a procedure, right? It's a procedural way to describe whether or not a certain signal is feasible. But actually what you want for this kind of application is you want some kind of analytic expression for what the feasible set is, right? So that's the next step. So can we describe the feasible set for this policy in an analytical way? It turns out yes we can. That's why I'm here. So we start with an observation. So if we see that if a certain reference is feasible, then we can also permute it, and it's still feasible, right? And that's fairly easy to prove. So any permutation of our feasible signal is still feasible. So somehow that gives a clue of how to kind of structure this massive space of potentially feasible functions, because this function space is a nasty thing to work with. But what we can do is, well, we can say we can characterize the feasible set in some way that is insensitive to permutation of signals, and we use this way. So how do we make it insensitive? Well, we integrate over all time, right? So we take a signal, integrate over all time. So clearly that's not sensitive to permutation. So what this thing is integrates the reference above a certain power level, right? So this simply, so we call it the EP transform. So it computes the energy requested above a given power level. That's what we can do. We can, I'll show you how we construct it. So here's the function again. So we take this power reference over here, it varies quite wildly over time, and we start constructing it. We say, okay, I'm going to draw a function here, this EP function from left to right, right? So at 0, how much power is being delivered above 0? Well, that's all energy. And then we go on and go on, and we get these points over here. And this way we've constructed the whole diagram, right? So every time we take the integral above this line, construct the diagram. So this has some really nice properties already. We can see that, well, this is a monotone convex function. That's nice by construction. Follows. This point up here, this intersection, is the total energy requested from the signal, right? Because that's simply integral of the signal minus 0. Fine. This is the maximum, the point at which it reaches 0 is the maximum power requested. So that's also nice, because that's the point at which it reaches, reaches the 0 here. So that's already some information we can read from this diagram immediately. That's nice. So that's the signal. That's the kinds of things that our system might be asked to do. But how can we describe the capabilities of the system? Well, we can, the idea here is to construct this signal. So this is a worst case reference, we call it, right? It's the just feasible signal. Basically, forget about this mathematics first. You run all the batteries at full tilt until one runs out, and you keep running the rest. So everything runs as long as it can for as much as it can. And what you get is a decreasing power level. So this is a large population of batteries. This is a uniform distribution over here. So you start out running at very, very high power. Well, yes, high given this small batteries. And then you decrease stepwise as each battery runs out of juice. You decrease the power level and so on. So you get this worst case reference signal. And you can then define its EP transform. So its EP transform has this, we denote by omega. So again, constructing that, we get a curve again. Right. Where this is interesting, so this is the amount of energy stored in all the batteries, this is the maximum power delivered by the batteries. Okay. Now there's a theorem, and now show you the intuition of this theorem, which says that, okay, we can compare these EP transforms, because remember what it does is it computes the amount of energy delivered above a certain power level, right? So if we say, well, if this is our request, this is our capabilities, if the amount of energy requested above a certain power level is always less than the amount of energy available above a certain power level, then it's feasible, and vice versa. The proof takes a bit longer than this, but you can see how this works. So what do? We take this, right? Stack of batteries, feasible, a request. We compute their EP transforms, we plot them, and we see, aha, this fails, right? So here, this is our capabilities, and this pinkish line over here is the request, and because this exceeds that, is not feasible. In fact, it asks for too much energy. Okay, so now we can come back here to our motivating example. We can plot for these three different configurations what is their EP transform. So which is actually best? We had quite a few C's, so indeed you can see here that yes, C is the most, is in this case the actual best configuration. C is better than A, C is better than B, but between B and A it depends, right? So that's with this kind of intuition, so that kind of shows the power of this kind of representation. We can quickly see what are the relative capabilities and whether something is feasible or not. Also, and we don't have a proper use for this, but intuitively it tells you something about what we call flexibility gap. So remember that this is the amount of power, maximum power we can deliver. This over here is the amount of energy stored in the battery. So you can say, well, if we had some kind of fleet or a single battery with those characteristics, it would be a straight line, right? So a single battery is always a straight line in this diagram. So we can say, well, the cost of heterogeneity is this difference somehow, right? So these are all the signals. In here will be all the signals that we cannot fulfill because we are heterogeneous. So that might be an interesting quantity for aggregators of large heterogeneous sets of devices. So the other application, final application of this kind of representation is you might look at scheduling indeed. So now we are the aggregator and we say, okay, we want to deliver pulses, right? So now we have a number of devices, here only 10, all the same amount of power, 1.5 kilowatts, and very short duration, right? So this is some kind of a very brief demand reduction or something else, between 0 and 20 seconds. But we just want to see, well, can we deliver kind of short 15-second pulses with this system? And if so, how much of that service can we deliver? So we can consider, this is a variable amount, right? Just 3 numbers plotted here, but it can be any number. So we want to kind of maximize how much power we can deliver in these 15 seconds. And again, we can just use that in this plot, right? So here on top you see the bound formed by this capability curve, the flexibility of our set of devices. And here you see these are simple requests, so there are simple straight lines. These are the various magnitudes of requests, so you basically optimize this against this bound, and that's how much you can deliver. So this is the way an aggregator could use such a representation. Okay, so to summarize this part, so we've had the control, now we have a representation of the resulting aggregate flexibility, which is necessary and sufficient. It summarizes the capability, but it also summarizes the power profiles, the requests made on this set. And it's convex and monotone. And you can use it as an instant feasibility check, or you can use it in various optimizations or to quantify this flexibility gap. Okay. So this was kind of operational planning stage, right? So you say, well, I can control something, I can then schedule that. Now we take this into an application which, well, materialized as we were doing this, which is the contribution of storage to system adequacy. So to do that, we have to look at the question of what do we do if a request is not feasible, right? So at some point we will get a request and sorry, we can't do it, right? It's too much power being asked. So we have to define some other policy, some policy that is results in something similar, right? So you get a request that's infeasible, you somehow need to take it back to a feasible set because that's all you can do. You can only do things that are feasible. And we define some kind of loss function between these two, and we say, well, we want to somehow minimize that. Right? We have a policy that minimizes that. And in this case, we'll use the energy not served, or unserved energy, as this loss function. Right? So we try to deliver a signal that is as close as possible in terms of unserved energy to the original request. So this is how we define that. So here we use gamma for that. So the loss function between these two is simply the difference. Right? And we assume we never deliver more power, because that would be silly, right? So don't ever deliver more than you asked for. Okay, so why is this interesting? The particular use case here is the GB capacity market, right? So here in Great Britain there is a capacity market which pays generators, but also interconnectors and also storage owners for their contribution to system adequacy. So in order to do so, you need to quantify what the contribution is of these resources to system adequacy in a sort of operation independent way, right? So this is typically done by kind of a perfect foresight or perfect dispatch, right? You optimize the amount of contribution they make. And then the question came up, once there was more and more installed battery capacity, this was done in the summer of 2017. There was a request. There was a lot of work going on that certainly Stan and Chris Dent and Amy Wilson were involved in. Is what is the way these batteries are actually dispatched? Because it makes a difference, right? So if they are finite energy capabilities, they say they can only run for 1 hour. Well, we shouldn't treat them equally with these large pumped hydro, the Norwick units, right? So how do we derate these units in an appropriate way? So that resulted in a lot of studies and a lot of ideas. Well, how should we simulate essentially these batteries in a simulation? How should we quantify this? There's various options that I won't go through in view of the time. But essentially there was confusion. What's the optimal strategy to minimize or to maximize the contribution to security of supply? And in this case, it was decided that should be how to minimize the expected energy unserved. So that's the background. Now it turns out that a straightforward extension of our policy also minimizes energy unserved. And to illustrate that, we'll come back to the same picture. We make a little extension. Now we say, okay, let's just create some fake negative capacity, right? So we can keep running. And we also create this extra battery which starts empty, but it's as large as we need it to be, and it can also keep running, right? And we just use the same policy. Basically, the policy says try to use the top left as much as you can, but sometimes move over to the right whenever you're short of power. So we start here, and now we go up here. This is a completely infeasible power level. It's above the maximum power that can be delivered by these batteries. So what happens is we end up in this region. So where do we draw power from? Well, this battery, this battery, this battery, and a bit of this virtual battery. So again, use some of each, and you draw some from here. And that's basically unserved energy, right? But we can basically extend the same policy, get these numbers. And it turns out, because our policy uses the top left whenever we can, it automatically minimizes the amount we draw from the bottom right. Therefore, it minimizes unserved energy. And therefore, our policy is, with a kind of same policy with a minor extension, works here, is also optimal in this sense. So that's what I mean by the star on saying we have to be a bit careful how we formulate it, but it's effectively the same thing. Now, turns out also this EP diagram comes in use again, because actually we can compute, again, this is the capabilities of a set of batteries. This is a request that's clearly not feasible because it's way above. But actually it turns out that the maximum gap between these two is some amount of energy, which is exactly the energy unserved by this policy, and we can prove that it's also the minimum energy unserved by any policy. So that's quite nice. So that means, okay, this would be a good candidate to run these types of studies with. The only problem is that those studies are always run in discrete time. So we get to the discussion we had yesterday morning, right? Discrete time policies and continuous time. So our policy is defined in continuous time. So what to do? Now it turns out we can define a discretization of this policy that inherits the optimality from the continuous time. And it's actually very straightforward, right? So you simply say, well, in our discrete time setting, let's pretend we're still continuous, but there will be piecewise constant requests coming in, right? So there's a continuous time signal, but it's piecewise constant. And then we see, okay, well, so what is the initial state and the end state of our continuous time policy over each of these small intervals? And then we say, well, given this initial point and this final point, let's now define a constant control over these periods, and that then is our discrete time policy. And then we of course check that it's feasible, and yes it is. So that actually solves the problem, and we have a discrete time optimal policy for this kind of energy that minimizes energy not supplied. Okay, so here's a brief construction, right? So I'll walk you through this picture. Okay, some of the backgrounds here have gone missing, but essentially you see here the same representation I had at first, right? So we have our batteries ordered in decreasing time to go. We then have a goal. We want to deliver a certain amount of energy, some power reference times delta t, where delta t is our step size. And we look at the left first. Basically what we try to do is we try to find the horizontal level in this picture for which the total energy we can draw from these batteries equals this amount. Now of course there's a maximum we can draw from these two batteries because that's 1, right? So we can only decrease at the maximum rate of 1. So is delta t, right, is delta t. So we cannot, there's a bit of shading missing. So we can draw at most this amount from these two batteries over here. So we start counting. Well, if that's not enough, we keep on going. This is the amount we want until the next one. We start drawing from this battery, keep going. Yes, we find the level we want. And then we say, okay, well, this is our target level. So try to discharge all batteries to this final time to go level. So this one runs full tilt until here. This one runs a little bit till there. That's our final policy. And then you can implement that to make an easy algorithm. There's something I've learned publishing things that are potentially complicated but ultimately simple. If you don't publish the algorithm, then no one will ever really implement it. I learned that the hard way with the fridges. It's a beautiful thing in the end, a lot of work, and in the end it's a very simple algorithm, but if you don't actually write the algorithm, then no one will actually do it. So here is the algorithm. I won't go through it now, but you can see in the paper if you're interested. So briefly, here's an example of how this works, right? So we have a, yes, let's Yeah, let's do this quickly. So again, we have a request over here that is supposed to be fulfilled using 4 different batteries. So the ones you just saw over here. These are 6-hour time steps, so now we're making very large steps. The batteries are as follows. We have initial states of 4, 3, 2, 1 hours, and battery powers are 5, 4, 3, and 9 kilowatts, right? So there's a bit of diversity here. We initially ask for 1 kilowatt for 6 hours. We compute the target time to go for these 6 hours at the end of the 6-hour period. That's 2.89 hours. We do that by running battery 1 at 930 watts, battery 2 at 70 watts, right? So there's a division at work here. And then we satisfy this first 1 kilowatt for 6 hours. Next step, we are asked to deliver 3.5 kilowatts for 6 hours. Okay, again, we do this algorithm, this one over here. We compute this target time to go 0.95. Again, we compute the various powers over here, run that, we supply all power. Then in the third time step, we run out of power, right? So our target is 0. We start, so all batteries here have equalized, our target is 0. We run them all at their rated power, and we end up still with some energy not supplied over here. And finally, the final time step, well, they start empty, it's gone. Is all we could do, and all this energy will be unsupplied. Of course, we can also do this with this EP diagram, which makes life much easier. We see this gap over here, 22 kilowatt hours, same as here. So instantly, we see that's the case. So we can apply this also, and I'm not going to ask you to read this, but to a simple GB adequacy study that we ran. So we did this model, kind of approximate Great Britain, bunch of power plants, wind, demand, some batteries, and see, okay, compare a few policies and see what their impact is to security of supply. And here's some examples. So we come across a lot of these things. So what happens here, I should explain here the setting. So we have this black line here, the top line is demand in the GB. This white bit is the part that can be supplied by conventional generators. And at some points, typically winter evening peaks, there may not be sufficient generators on the system because, usually because there's a larger than normal number of failures. So we rely on batteries. And then we can look at this residual request. And then we can, here we draw the EP diagrams for those cases. So sometimes they're feasible, right? So this is the capabilities of our batteries. This is the request, it's fully satisfied. Sometimes they're completely infeasible. Sometimes, these are the interesting cases, they would be feasible in terms of energy and power, but they're not because of the heterogeneity of the battery. So there's these kinds of curves. So we can run these simulations, get a lot of results. You could ask more questions about this later if you like, but basically, going from no storage, this is the number of loss of load expectation. This is the loss of load expectation, is the number of hours that we are typically unable to satisfy demand on average. So that goes down obviously with batteries. Again, we tried a few policies. This one's optimal, and this is in terms of energy not supplied, and we see that this is smallest of all policies in this case. And I can explain about the uncertainty ranges, but this does prove something. Okay, so to summarize, we have this myopic policy, which also minimizes unserved energy. It's not unique in doing so, but it is unique in being myopic and being greedy, right? So there are other ways in which you could minimize unserved energy, but this is an easy one. The EP diagram works again to quantify unserved energy, and we have a discrete time policy that you can actually use in simulations. So you can use that for discrete time aggregator scheduling, or you can use it for these kinds of adequacy studies, as I've just shown. So to summarize the whole talk, greedy policy that maximizes instantaneous available power, time to infeasibility, future flexibility, unserved energy, or minimises unserved energy, I should say. We have given this aggregate representation of flexibility, that's analytical, which is nicer to work with than a procedural form, and a discrete time algorithm. So next steps are to see, well, to consider this optimization step in more stochastic scenarios. So we've done some preliminary work on that. That's actually, that's very promising. Also to continue this last route on the capacity value calculation, right? The capacity contribution of storage to security of supply, to do some further results there. But finally, the big elephant in the room, of course, is recharging. Recharging and including cross-charging, right? So sometimes if you have a very heterogeneous set, it may be beneficial to actually draw some power from some of the large, high time to go devices and put it into the low time to go devices, even if you have efficiency losses on the way. And of course, all of this very nice kind of set theoretic results where we don't care about the probability of future events because it's optimal in a general sense, that goes out the window. And we need to somehow do some either explicit modeling or some learning to say something about this case. And with that, thank you.
They are switching off the line. No.
Oh.
Okay, thank you.
Thank you.
So first, erase this hand first, and then why? Yeah.
So you said that your charging policy was the inverse of your discharging policy. So you charge the batteries with the shortest time to go first.
In this, you were paying attention to this slide, yes.
Yeah, so I got there before you said it because it's sort of obvious. So in a deterministic world, you end up with all of your batteries having the same time to go after a few charge and discharge cycles, and therefore they behave like a single homogeneous battery because they've got the straight line property.
Yes.
In a probabilistic world, the real world, you then end up, I think, at any one moment in time with a target time to go charge state for all the batteries, and some of them are above it and some of them are below it.
Mm-hmm.
You then have some questions about the contingent cost of restoring the state, including losses and the actual arbitrage costs of the energy over time.
Mm-hmm.
I would encourage you very strongly to build a combined system services model all the way from frequency response to arbitrage, because I think that's what you're working towards.
Yeah, working towards is probably the right wording. There's a lot of steps to be taken. A few comments along the way, I guess. So first, yes, it seems obvious that this inverse policy is optimal if, for example, you assume that they're all equally efficient, right? So that's another thing, right? So, but let's assume they're all equally efficient and they can all charge at the same rate as they discharge and all that, right? Even then, that's not truly the case. So consider this. That's, I think, the simplest example. Suppose I am an electric vehicle, right? So I'm an electric vehicle. I have one large. I
agree.
Then actually, so I have two identical batteries, one with a large time to go and one short, right? Then, if I were to use this policy, I would run this battery first, right, to equalize them. Now, if I know that I'm going to have a very short window for recharging only, actually that's not what I want to do. Then I want to run both batteries, because once the opportunity for recharging comes, like I say a fast charger, then I want to actually have scope in both batteries to recharge both simultaneously. So there's the discharging policy is going to depend on the charging.
Where there are both local constraints, for example, the batteries are located in the same distribution system, and therefore you have a power limit for charging and discharging them all at the same time. Particularly where there are other uses of the battery, and the electric vehicle is the canonical example, then you have to consider, then you have an intelligent agent problem.
Mm-hmm.
The local controller has to decide based on the central signal and the other information what the penalty function is for charging or discharging, which is more than just the system value.
Yes. No, but but all kind of value calculations are not yet present here. So they will be important for this, for any charging scenario. But the charging will also, will also affect the discharging. You want to be ready for the desired charging pattern, right? So there's this interaction which is going to make things really complicated. But in general, I agree. We'd love to make this a generalized kind of, this is how you run batteries. But yeah, it turns out, so that was actually our initial intention, like, let's spend 2 weeks on doing this, and then we'll move on to interesting cases. And it turns out that actually there's quite a bit more depth in here than we thought there was. Yeah, thanks.
It seems that your model, I love your heterogeneous batteries. I've worked in this area as well. But it seems like you have homogeneous power demands. But in a real network, it's not homogeneous at all. You'll have periods where you have very high power demands and you have to draw from high power devices or discharge or inject from high power devices. So your simple rule wouldn't apply there.
You would. So it would.
There's going to be periods where you're going to, like you may have a lower power demand where you could choose a high power device.
Yes.
But you don't want to because you have to reserve the high power devices for times in which they are needed.
Yes, absolutely. So that's exactly what we do. Maybe sorry if I wasn't clear. So we sort the devices, high or low power, that doesn't really matter, by their time to go, right? So we divide energy by maximum power, so that's time to go. So we say whenever possible, high or low power device doesn't really matter, but we use the high time to go device, right? So that whenever so kind of signals come in have to be put along this axis, right? So if a signal comes in that's close to 20 kilowatts here, we have to use all batteries.
I see. So in other words, you apply this rule within the set of devices that satisfy the power rating.
Yes, we start basically from the left. So we say if we only use, so this, if we get less than 10 kilowatts, we're not going to touch this battery. We only use these two batteries because we want to.
It seemed like you had a plot later that showed that a homogeneous fleet was better than a heterogeneous fleet.
Oh, no. So there,
What's that?
it was the fleet versus the signal requirements. So we had a homogeneous fleet, I should say this. Clicking, right. So here was a homogeneous fleet, right? And that gives rise to this transform. Go on. Yeah, here we go. So this homogeneous fleet gives rise to this transform over here, and there was this signal over there, which is some sort of white noise.
But you had another one where you had a line like this and lines like this, and the homogeneous fleet dominated.
Ah, this one.
Yeah,
This one, yes.
If you go one or two more slides later, yeah, there we go.
Right. If I were to have a single, so this is the capability curve of a set of batteries. If instead of this the yellow or the blue one, right? So if I would have a single device or a fleet of identical devices with this power rating and this energy rating, this would be their
A
curve.
high-powered device is going to be expensive. That's why you want a heterogeneous fleet.
Yes.
So
So exactly. So what you then have to do is you have to characterize. So this is your capabilities. You could characterize the kinds of requests you expect, right? If you only infrequently expect high power requests, your request curve will be somewhere down here. Will be some kind of family of stochastic. So this is kind of the stochastic application. You could say, well, what are the kinds of requests I can imagine? You can make some probabilistic model, do some simulations perhaps, draw a number of curves, and you might conclude that yes, making every device high-powered, getting this curve is expensive. This blue curve is much cheaper, right? Has the same, it can handle the same peaks, just not very long, and has the same total energy, so it can supply low power over the same time, but it cannot handle anything in between. The question is, what's the power density in there? If there isn't much, pick blue.
I give time for others.
Yes, Simon. Yeah, thank you very much for the presentation. So I'm wondering about the aging process.
Yes.
So in this case, you are using more or less the same battery all the time.
Ah, yeah.
So and even the initial case, is there very different remaining life? How do you?
True.
And is it possible to integrate that somewhere? So not. I think this policy will push to use always the same batteries. So.
Yes. No, it clearly wants to use, it wants to maximize this set of possible future actions, but it doesn't take into account value. I think once once you look at the larger picture of, you have to make some kind of value or cost function or something, and then that can maybe be included as an additional parameter. But you basically choose to be suboptimal in this sense, right? You're taking a risk by not. Yeah, you're effectively taking a risk by not running this battery first, which may be justified over the long term, but you have to really weigh the risk of, not supplying some power reference in the future against saving on your battery performance. So there's a bit of a trade-off, and you have to see whether it also depends who's in control. I think if you would say that in some sense it doesn't matter if you wear out one battery first, if that means the other ones last longer, if you're in charge of all batteries, right? So you could make that argument, but I guess it's non-linear, right? It's probably non-linear. So
Not true event for them.
exactly. So, or if there's some natural decay anyway, but that's something to consider, yeah. But it will probably have to go along with the more economic formulation of such a problem. But still, we hope that at least these kinds of technical constraints. So even if this is a kind of a toy model, we hope that this can kind of serve as a number of sense checks or constraints on economic dispatch, right? You would there's certain things that you wouldn't want to do, right? There's some things that are generally smart and some things that are generally not, and you would only want to do things that are not smart from this perspective if there's a genuine economic advantage to not doing that, right? Yeah.
There was first green, and then we already speak, but we did not.
A very quick question, because you said you want to minimize energy non-served, but maybe that's not what you want to do.
That's true. So there is actually some. True. So, well, all things being equal, you probably want that, but it might be. So, for example, there's comments here. So we had a discussion with James and Stan, and they remarked one of the things that is really the case.
Is the cost of a service interruption may depend in a non-linear fashion on the
Exactly.
durations and the importance of power interruption.
Exactly. So you could say that the first, say in this kind of grid scale examples, the first 100 megawatts is free, and then the first, or almost free, and then it kind of increases in a non-linear way after that. So that's a case that kind of they also mentioned in the research. It's definitely something that, I think there's some of this strict greedy optimality probably goes out the window as well. But yeah, you're right. There's a good case for that. Although currently in a regulatory sense, that's not the case, but arguably it should be. Yes.
No. So, no more questions. So let's thank you then.